In enzymology, we are interested in the rate of a reaction, how fast the substrate is converted into product, whether the substrate binds tightly or loosely to the enzyme, which step is rate limiting if more than one step is involved in converting substrate to product, and whether any intermediate is formed during the transformation of substrate into product. By measuring the enzyme velocity at various substrate concentrations, the resulting plot can be used to provide information about Vmax, Km, and kcat. First, we examine how Vmax can be determined from this plot. The V versus S plot at a fixed amount of enzyme produces a hyperbolic curve, as shown here. It should be emphasized here that, to be meaningful, a fixed amount of enzyme must be used throughout the experiment. This fixed amount of enzyme corresponds to ET, the total enzyme present in the reaction mixture. As the concentration of substrate in the reaction mixture increases, the velocity also increases gradually. However, because a fixed amount of enzyme, for example 10 microgram, is used in the reaction, further increases in substrate concentration will eventually lead to saturation of the enzyme. At saturation, all of the enzyme active sites are occupied by substrate in the form of ES complex. Further increases in velocity are not possible. Thus, a Vmax of 1 arbitrary unit per minute is obtained. Note that Vmax is defined as and is equal to ET multiplied by kcat. The enzyme velocity depends on the total amount of enzyme present in the reaction mixture. Thus, if a decreased amount of enzyme, for example, 5 instead of 10 microgram, is used in another experiment, a lower Vmax value will be obtained in the V versus S plot. Next, let us examine how Km can be obtained from this plot. Km is defined as the substrate concentration at which the reaction velocity equals half of Vmax. Thus, a Km value of 0.05 millimolar can be obtained from this plot. Km is equal to the sum of K minus 1 and kcat divided by K1. For a catalytically sluggish enzyme, kcat is relatively small compared to K minus 1 and can therefore be ignored. In such a case, Km equals Kd, the dissociation constant at which half of the enzyme is free and half is present as the ES complex. Because half of the enzyme is present in the ES complex, the reaction velocity reaches half of Vmax. Km informs us about the binding affinity of an enzyme for its substrate, that is, how tightly the enzyme binds the substrate. A lower Km value indicates tighter binding between the enzyme and the substrate. Last is the kcat. By definition, Vmax is equal to ET times kcat. Vmax alone does not reflect the catalytic efficiency of an enzyme because it depends on the total enzyme concentration present in a reaction mixture. Kcat, on the other hand, is a true catalytic constant and informs us how fast an individual enzyme molecule converts substrate into product. In the plot shown above, enzyme amount is expressed as microgram of protein. Enzymes come in different sizes and have different molecular weights. By analogy, people vary in size and weight. Thus, it is more informative to express work done per person rather than work done per kilogram of body weight. Thus, to obtain kcat, one must convert the mass of enzyme in milligram into moles of enzyme, as follows. Mole of enzyme can be obtained by dividing the enzyme mass by its molecular weight. Upon rearrangement of the above equation, kcat can be determined as follows. For example, if Vmax is 200 moles of product formed per minute and ET is 5 moles of enzyme, kcat then is equal to 200 per minute divided by 5, giving a value of 40 per minute, or 40 divided by 60 seconds, which gives 0.67 per second. In enzymology, kcat is also known as turnover number, the maximum number of substrate molecules in enzyme converts in a product per active site per unit of time. Let us now examine other constants encountered in chemistry and physics. By comparing the catalytic constant to these constants, we may gain further insight into the meaning of kcat. Equations found in various areas of physics and chemistry are shown in this table. In physics, for example, Einstein's theory of special relativity states that E equals mc squared. By comparing this equation to the general form y equals mx, the value of the slope m can be obtained from a plot of energy versus mass. In this case, the slope m turns out to be a constant equal to the square of the speed of light. Similarly, in the Beer-Lambert law in chemistry, the absorbance A is equal to a constant multiplied by the concentration C. From the plot of absorbance versus concentration of a molecule that absorbs light, a constant known as the molar extinction coefficient, epsilon, can be determined from the plot. Each chromophore molecule has a unique capacity to absorb light, as specified by the value of its molar extinction coefficient. In enzyme kinetics, a plot of Vmax versus ET, expressed in moles of enzyme, produces a straight line. The value of kcat can be obtained from the slope m. Similar to the relationship between the molar extinction coefficient and a chromophore molecule, each enzyme has a characteristic cat value that reflects the rate at which it converts substrate to product. Thus, a human DNA polymerase has its own distinct kcat value, which differs from that of a monkey DNA polymerase.